In the beginning of weapon history, there was the word, and very little more. Then progress set in. Through the centuries, man has increased the effective range and efficiency of his weapons as rapidly as his science would permit.
Another important section of the thermal program was a study dealing with normal city vulnerability to fire started by atomic weapons. 3 cubicle houses, 7,700 feet from zero, were erected for one phase of this study concerned with exterior kindling fuels. The first house has a clean, safe yard, but dry rot is working in the unpainted siding. No rot here, but toys, weeds, and trash against the fence. A clean yard, painted fence, and maintained siding. Number 9 goes off. 13 calories per square centimeter. Overpressure, 3.5 pounds per square inch. Time sequence photography shows the results. Destruction on the right from the yard trash which set fire to the fence. On the left, rotted wood in the siding was the ignition point. Sound painted wood and a clean yard allow the center house to survive. The fire hazards in these projects are not unusual either. 6 big American cities were inspected to ensure that representative conditions were tested. Conditions which suggest that a bomb of even this nominal power could start more than 100,000 fires over 25 square miles of urban area. We come now to the biggest program, the primary reason for Shot 9, the first effect shot. The biggest program in sheer volume, in theoretical predictions confirmed or refuted, and in the mass of empirical knowledge gained. 28 separate projects came under this heading, beginning with basic measurements on simple cylinders and rectangular concrete slab structures in a number of orientations. These passive targets, heavily instrumented, were not designed for response by displacement, but only to record shielding and loading factors at various heights and aspects. The findings of this important job can now be extrapolated for prediction of blast loading on a great variety of targets without direct testing. A truss bridge section 2,300 feet from zero. Shot 9 produced a small permanent set in the top chord with an overpressure of 11.5 pounds per square inch. But the mock stem had not formed to reach the height of the bridge. 8.5 pounds did this on Shot 10. Apparently, for wind or drag-sensitive targets of this type, a low burst is more damaging than a high burst at similar peak pressures. A test of Army prefab Bailey bridges. Shot 9, 4,100 feet from zero. Essentially undamaged, the bridge slid back on its piers as expected, moving 43 inches from a peak pressure of 8 pounds. 9 pounds from Shot 10 hits another bridge. Movement out of all proportion to that caused by almost the same static pressure on the first shot. Army equipment, which included 54 trucks and jeeps, was exposed to Shot 9 pressures ranging up to 21 pounds to the inch. Thermal input reached 130 calories per square centimeter. Damage was generally moderate, as expected. All but 2 vehicles, one with burned tires and one with a missile-punctured radiator, could be driven away under their own power. For Shot 10, Army tanks, artillery, and 22 trucks were exposed to pressures expected to range from 3 to 55 psi. Once more, damage was much greater than expected. Equipment was not merely overturned, but often torn to pieces or hurled great distances, at overpressures from which no such effects were predicted. Pressures which had done negligible damage to identical items on Shot 9. Obviously, Shot 10 was handing out surprise data. It was evident that our old static pressure criteria were not valid for predicting damage to wind-sensitive targets. Standard command posts, foxholes, and machine gun positions were located on Shot 9 at 600, 800, and 4,000 feet from zero. Overpressures 8 to 22 pounds to the inch. General analysis indicated that cover-supporting timbers began to fail at 8 psi, while revetment stood up to around 20 pounds. Conventional sandbags tended to catch fire and spill their contents. One interesting finding was that foxhole covers can greatly reduce inside pressures, which may otherwise build to twice the outside pressure. For Shot 10, Army personnel buried 1,200 live mines and 2,000 indicator mines in a field extending 2,700 feet from zero. Burial depths down to 15 inches appeared to make little difference. The blast detonated 100% of the live M15s and M6 mines out to 1,300 feet, where surface pressures were 20 psi, and the M14 mines detonated out to 1,650 feet in the 12-pound region. 6 Marine LVTs, landing vehicles tracked, at distances from 800 to 4,500 feet from zero, with pressures reaching 22 psi, 2,400 feet. Overpressure 11 pounds. Damage was light on all vehicles. On Shot 10, the same vehicles varied from 1,000 to 3,450 feet from zero, pressures running up to 47 pounds. Shot 10 damage was again unexpectedly heavy as compared with Shot 9, with 1 vehicle destroyed and 3 severely damaged. These tests suggest that normal shock waves from high bursts will damage LVTs only moderately up to 22 psi, while low bursts will do severe damage above 12.5 pounds. Curtain wall panels on a series of concrete test cells, some with window openings, some without. The panels were constructed of various masonry materials such as brick, cinder block, clay tile, and combinations of these materials. Similar variety went into roofs and interior partitions. On Shot 9, 4.5 pounds overpressure does this, 6,700 feet from zero. 7 pounds here, 4,400 feet range. Unreinforced brick stood up fairly well, though cinder block and transite shattered. Walls with 20% window opening showed much greater blast resistance than blank walls, though damage to interior partitions was high. 3 frame structures with windows and skylights containing various types of glass and plastic glazings were set up at 7,600, 12,500, and 20,000 feet from Shot 9. Pressures were 4 psi or lower. A few conclusions that can be drawn now are that quarter-inch clear plastic shattered least of the material tested. Quarter-inch wire mesh was the largest mesh effective in reducing interior missile hazard. Exterior jalousies were worthless, and explosion hardware has very limited usefulness and may even be disadvantageous. Signal Corps placed radial and transverse pole lines, underground wires, and aluminum towers at different distances to test damage effects and determine time required to restore communication facilities. On Shot 9, pressures of 7 to 9 psi knocked down the transverse pole lines at 3,500 and 4,500 feet, and partially destroyed lines at 5,500 feet in the 5-pound region. However, radial pole lines end on to the blast were almost undamaged. Similarly, towers at 3,400 and 4,400 feet were knocked down, and the one at 5,400 feet heavily damaged. At 6,400 feet, the top section of this 240-foot tower was made unsafe by 4.5 psi. Shot 10 damage to these installations was much heavier. The blast winds destroyed even the radial pole line to 2,500 feet, with static pressures by which it was undamaged on Shot 9. Air Force, Marine, and Quartermaster POL installations were given extensive testing. The major items were 5 and 55-gallon drum stacks, bulk storage tanks, and various subsidiary items such as can cleaning, metering, filtering, and pumping equipment. In general, Shot 9 damage was light or insignificant. There were minor gasoline fires. Drum and can stacks were scattered slightly in the maximum pressure areas, around 16 psi. 2 collapsible 900-gallon tanks were ruptured by 11 pounds at 2,600 feet. On Shot 10, results were unexpectedly violent. All stacks disintegrated, with cans and drums thrown hundreds of feet and left flattened or badly crushed. All marine fuel handling equipment was destroyed except one collapsible tank. Almost complete destruction occurred at better than 2,000 feet, at the same pressures that did trivial damage on Shot 9. A study of tactical importance. 145 ponderosa pines set in concrete, approximately 6,400 feet from Shot 9's 0. Instrumentation was thorough. A few major types being pressure gauges at 3 heights, time recording anemometers, pitot-type dynamic pressure detectors, and snubber wire arrangements to measure deflections. Pendulums were substituted for the lollipops of former operations to provide mechanical simulation of tree response. As on many of these projects, camera stations were set up to provide high-speed motion picture coverage of blast effects. Thermal input, 18 calories per square centimeter, resulting in only mild char on tree trunks, since the normal ground litter that will ignite at around 3 calories was lacking. Static pressures around 4 psi. Post-blast survey indicated that approximately 20% of the trees were broken, and the missile hazard from falling trunks and limbs would be substantial. There was scant reduction of static pressure inside the stand, but a 20 to 40% reduction of dynamic or drag pressures. Thermal shielding proved excellent, with negligible penetration beyond the 4th row of trees. 16 items of Army rolling stock were exposed on Shot 10 only. A 45-ton diesel locomotive, 1 riveted and 1 welded steel tank car, 13 boxcars loaded and unloaded of various types, 6,600 feet, 2 pounds overpressure, 4,400 feet, 4 psi, 1 empty boxcar turned over, 1 loaded car damaged, 3,400 feet, 6 psi. Boxcars damaged or overturned, 2,800 feet, 7.5 pounds, 1,850 feet, 9 pounds, 1,500 feet, before being hit by 13 pounds to the inch. And here's the same view afterward. The frame of one of those tank cars was thrown against a building 200 feet away. A tank car body went 1,200 feet.